Welcome to The Explainer. Today, we're diving into the world of cybersecurity to see how machine learning is basically becoming the Sherlock Holmes of the digital age, hunting down cybercriminals in ways we never thought possible. So, let's just start with this question right here. Because this isn't some hypothetical brain teaser, this is the reality for cybersecurity experts every single day. Seriously, try to imagine searching for one specific grain of black sand on an entire massive beach. That's the kind of scale we're talking about here.
And just to make it even crazier, that beach gets bigger every day. We're talking about a tidal wave of new threats. Security labs find around 450,000 new malicious programs daily. And these aren't just simple viruses anymore. No, this is sophisticated ransomware, super stealthy spyware, Trojans built to drain your bank account. The sheer volume is it's mind-boggling. There's just no way any team of humans could ever keep up with that.
And all of this brings us to this fundamental shift in how we have to think about security. The old way was to just build a digital fortress, right? Make the walls higher, the moat deeper. But today's threats, they're more like spies. They're designed to find the tiniest crack and just slip right through. So we need a totally new strategy.
Here's the most important point. Traditional antivirus software is reactive. It basically waits for a known bad guy to show up at the door. But what we really need is a proactive digital detective, something that's already inside the walls, actively hunting for clues, looking for suspicious behavior, and stopping threats before they can do any damage.
So who is this digital detective? Well, our hero in this whole story is machine learning. It's a type of AI that lets a system learn from tons of data, spot patterns, and make decisions on its own, with very little help from us humans.
And what's really cool is how our detective works. It basically has two main jobs. The first is anomaly detection. It spends its time learning the normal rhythm of a system, what everything is supposed to look like. Think of it like a security guard who knows every single employee, and the second an unfamiliar face walks in, an alarm bell goes off. The other job is classification. This is where it learns from a giant library of past cases, all the known viruses and all the known save files, so it can instantly look at a new file and sort it into a good pile or a bad pile.
So how does our detective get so smart? Well, just like any good investigator, it has to go through some really intense training. It has to study all the old cases to get ready for what's coming next.
And the training follows this pretty clear four-step process. First, you got to prep the data. Then you split it up. About 80% is used for the training itself. That's like our detective studying thousands and thousands of old case files. The other 20%, that's held back for the final exam. That's where we test if the detective can actually apply what it's learned to brand new cases it has never, ever seen before.
Now, getting this training process exactly right is absolutely critical. This quote here points out a huge mistake people can make. It's about something called scaling, which is just a fancy way of saying you put all the numerical clues on the same scale, like converting everything to inches. Well, if you do that before you split the data for training and testing, you're basically letting the detective cheat and peek at the answers to the final exam. Information from the test leaks into the training, and you end up with a model that looks way smarter than it really is. It's a huge problem.
If the training is too lazy or too simple, the model underfits. This is like a detective who only learns one rule. Criminals wear black hats. I mean, sure, it's simple, but it's going to miss every single criminal who isn't wearing one. It just doesn't get the big picture.
On the flip side, if the training is too specific, the model overfits. This is the detective who has memorized every single tiny detail of every old case file, right down to the color of the getaway car's hubcaps. The problem is, when a new case comes along that's just a little bit different, our detective is completely lost because they're still looking for those exact same hubcaps. So the goal, the sweet spot, is a good fit. We want a detective who understands the general principles of a crime, not just the tiny details of old cases. It can take what it's learned and apply that knowledge to new, evolving threats out in the wild. That's what makes it effective.
Okay, but before our detective can even start analyzing anything, all that raw evidence, things like messy system logs or network traffic, it has to be turned into clues that it can actually read and understand. And that process is called feature engineering. You can think of it as the art of translating raw data into structured numerical features. For instance, you take a vague log entry like a user logged in and turn it into concrete data points. What time was the login? What was the location? How often does this happen? These become the actual clues our detective gets to work with. All right, the training is done, the clues are all prepped.
Let's see our digital detective in action on a couple of real-world cases. This is where it gets fun.
Okay, case number 1, the suspicious login. So our model is constantly watching the server logs, just learning the normal rhythm of the network, who logs in, from where, at what times. It builds this baseline of what's normal. Then, all of a sudden, it sees something that totally breaks that pattern. Hundreds of failed login attempts for one user account, coming from a strange IP address at 3 a.m. Bingo. It instantly flags this weird behavior, identifies it as a classic brute force attack, and automatically blocks that IP address before the attacker has any chance of getting in. Case closed.
Next up, the digital fingerprint. So every single file on a computer has this unique signature called a hash. Think of it like a one-of-a-kind serial number. If you change even one tiny bit in that file, the entire hash changes completely. So when a new file comes in, say from an email attachment, our detective instantly calculates its hash and checks it against a massive global database of fingerprints from known malware. If it finds a match, well, that's like finding a criminal's fingerprints all over a crime scene. The file is immediately identified as malware and thrown into quarantine so it can't do any harm.
So after all that, what's the big takeaway? What does this all really mean for the future of how we defend ourselves online?
Well, we are smack in the middle of a huge shift. We're moving away from just building a fortress and waiting for someone to attack it. Instead, we're deploying these intelligent, adaptive detectives inside our networks that are constantly hunting for threats, learning from everything they see, and getting smarter and smarter over time.
And that leaves us with one last, pretty critical question for the future. We've seen just how powerful our digital detective can be, but what happens when the attackers start building their own AI to create smarter, sneakier malware? This is setting the stage for a brand new kind of arms race, a digital war fought between intelligent machines. The question is, who's going to win? And honestly, the answer to that is probably going to define the next decade of cybersecurity.